Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to this lecture. In the last lecture we studied the basic principle of experimental model analysis. In this and the next few lectures we are going to study FRF measurement using impact hammer, and in this particular lecture we are going to basically talk about excitation of the structure using impact hammer. So the topic today is excitation using an impact hammer. So a brief outline of the lecture is as follows. First we will look at a typical experimental setup that is used for FRF measurement using impact hammer. Then we will see that how FRF is estimated using transient excitation. Okay, because impact hammer basically applies a transient force and a transient response is generated. So how transient force and transient response basically can be used to find the frequency response function. Then we will look at the basic construction of an impact hammer, and then at the end we will look at the role of hammer tips in FRF measurement. So therefore let us first of all look at a typical experimental setup used for FRF measurement using an impact hammer. So a typical experimental setup for FRF measurement using an impact hammer, right. Let us look at this. So let us say we have a structure something like this. Let us say there is a frame structure. This is the frame we have. The frame is grounded at the bottom, and then we want to perform model testing on this. So to measure FRF we are using impact hammer here. So we will have hammer like this, right, which will be used for application of an impact force and measurement of that force. Okay, so this is the impact hammer, and then we have an accelerometer like this, let us say. So this is used for measurement of response, and often an accelerometer is used for measurement of response. The outputs of the hammer and the accelerometer, they are now passed through charge amplifier. So we have the outputs passing through charge amplifier. Like this. So therefore hammer has got a force transducer, which is typically a piezoelectric force transducer. This piezoelectric force transducer generates an output charge which is proportional to the force being applied. Okay, so the output of the hammer is typically a charge signal, and this signal basically needs to be converted to a voltage signal. Okay, this signal is a high impedance signal, and it needs to be converted to a low impedance signal, which basically leads to conversion of the charge signal to voltage signal, and this is achieved via charge amplifier. So charge amplifier converts the charge signal into a voltage signal. So then you of the output of the charge amplifier, which is a voltage signal, that is then fed to a data acquisition system or an FFT analyzer. So, let us say if we are using an FFT analyzer to measure this voltage signal, then we require at least 2 channels, okay, for measurement, because we want to simultaneously measure the force signal as well as the response signal. So, we require at least 2 channels in the data acquisition system or the FFT analyzer, which one we are using. So, we require a dual channel measurement. So, this is the output of the charge amplifier giving us a voltage signal proportional to the force, and then we have the output of the charge amplifier, which is amplifying the output of the accelerometer and giving us a voltage signal proportional to the acceleration, like this. So, this FFT analyzer basically has got inbuilt functions to process these signals, right, and one of such functions is the frequency response function, okay. So, we can directly estimate the frequency response function based on this 2 signals, like this, okay. So, therefore, this is nothing but, let us put nomenclature here. This is the test structure, this is impact hammer, and this is accelerometer, and this is FFT analyzer, or it could also be a data acquisition system, any DAQ system, right. Now the force transducer used in the hammer and accelerometer, if they are of charge type, right, that is the output of these transducers are charge signals, then we require an external charge amplifier as shown in this schematic, right, for amplification of the signal or conversion of the signal from charge to voltage. But nowadays the sensors which have built-in charge amplifiers, the electronic circuits which performs the conversion of charge signal to voltage signal, nowadays we have the sensors which have that built-in circuitry. The sensors themselves are having that circuitry built into them, and therefore such sensors are typically they are referred as IEPE sensors or ICP sensors. So, we have IEPE or ICP transducers, right, that is the force transducer and the accelerometer. So, they have built-in charge amplifiers, right. So, IEP stands for integrated electronics piezoelectric. So, it is basically name of the technology, right, for the having a built-in charge amplifier, and ICP is another trade name which basically also indicates sensors which have built-in charge amplifiers. So, these basically sensors, therefore, their output would be directly in terms of a proportionate voltage signal, right, and therefore, the sensitivity of these transducers, they are in terms of, if it is a force transducer, then the sensitivity of these transducers will be in terms of millivolts per Newton of force, right. If it is an accelerometer, then the sensitivity of this ICP or IEP type accelerometer would be in terms of millivolts per meter per second square, or millivolt per g of acceleration, 1 g of acceleration, right. So, therefore, such transducers, if they are there, then we do not require external charge amplifiers, right. We can directly feed the output of these sensors to the FFT analyzer. But these sensors, they also require some power supply for them to operate, because that built in charge amplifier requires power, electric power, and therefore the input ends of the FFT analyzer, they must be have the capability to supply that electric supply, okay, electric power. Otherwise we require a separate source in the form of a signal conditioner which can supply that electric power. So therefore when we are using these types of IEP or ICP type of sensors, we should also ensure that the data acquisition system has the capability to supply necessary electric power for the sensors to operate. So therefore if the sensors, they are of charge type, so we have charge type transducers, right. So in that case the force transducer sensitivity would be in terms of picocoulomb per Newton, right, and for accelerometer the sensitivity will be in terms of picocoulomb per meter per second square or picocoulomb per g of acceleration, 1 g of acceleration, right. So in either case in the FFT analyzer what we get basically are voltage signals which are proportional to the force and acceleration signals, right. So let us try to talk more about what are these signals. So let us go to next page. So if we look at, let us say what are the physical signals, let us try to sketch physical signals here, right. So the force signal will be in terms of, we will have a force time history. So we have the force in terms of newtons, and then we have time t here in terms of seconds. So this force will be in the form of an impact being applied. So it will be basically a narrow pulse, right, which is acting on the structure. So we have the force will be in the form of a narrow pulse like this, which is acting on the structure, right. And then we will have similarly for the acceleration, let us say this is the acceleration A in terms of meter per second square as a function of time. So structure is going to have a transient response, okay. So the response will build up as the force is applied, and then gradually it will decay, because there is no longer any force acting after the pulse has elapsed. So we will have the transient response like this, something like this, right. So this will be the acceleration of the structure. So these are basically the physical signals. Now what are the corresponding measured voltage signals in the FFT analyzer? Let us write them here, measured voltage signals, right. So for force signal F, we will have the voltage signal Vf as a function of time, right, that will be available to us. And then for the acceleration we will have Va voltage signal, right. So F and A subscripts are used to indicate the force and acceleration. So these are the voltage signals that will be measured in the FFT. And now how can we retrieve the force and acceleration signals, right, or how can we convert these voltage signals into engineering units, in the signals with engineering units? So we can also obtain measured signals in terms of engineering units, okay, and that we can obtain using the sensitivities of the corresponding transducers. So if you represent the measured signal in engineering units as say f of t, then this would be nothing but Vf of t, that is the voltage signal corresponding to the force, divided by the sensitivity of the force transducer. So let us say Sf is the sensitivity of the force transducer. So in this way I will get this signal in terms of newtons, right. Similarly if I wish to know what is the acceleration signal, which is A of t, the signal in the terms of Inching units, then I can divide VAT by the sensitivity of the extrometer, and this should be now in terms of meter per second square, correct. So, we should know that the sensitivity of this SF is in terms of, let us say if we are using the IEP or ICP type of transducers, then in that case the sensitivity SF would be here simply the volts per unit Newton, right. And since the voltage Vf is in terms of volts, this ratio uses the force in newtons. Similarly, this extrometer sensitivity is can be written as in terms of volts per meter per second square. So, in this way, you can see we obtained a measurement of the force and excitation signals in the FFT analyzer. Now, how we obtain the frequency response function from these measurements. So, let us look at FRF measurement, or rather FRF estimation, okay, based on these signals. So, what we note that we now have a measure of force signal given by f of t, and this force signal is a transient force signal. It is a transient force, it is acting for a short duration, right, and after that there is no force. So, it is a transient force, and then it leads to response excitation A of t, which also is transient. So, it is a transient response, correct, and so therefore transient force leads to transient response. So, the question is, how do we find the frequency response function? In fact, if we recall, we defined a frequency response function in terms of the harmonic force being acting on the structure, right. So, we said that the frequency response function at value omega basically is nothing but the response of the structure, okay, to a unit amplitude harmonic force. So, fundamentally the frequency response function is defined for harmonic forces of different frequencies. So, how we obtain the frequency response function using transient force and transient response? The transient force and transient response, they are not harmonic, nor they are periodic, right, they are basically aperiodic functions. So, how do we obtain the frequency response function from this? So, here therefore, we make use of the Fourier transform which we studied earlier. So, Fourier transform enables to describe the transient signals in the frequency domain, right. So, once we go to the frequency domains, they again basically are represented as sum or collection of different harmonic signals. So, therefore, we take the Fourier transform and that basically gives us a frequency domain description of this transient force. Let us represent it by f of omega. Similarly, the excitation signal is Fourier transformed which basically uses the frequency domain representation of the excitation signal A of omega, okay. So, and let us say that we on the structure we have applied the force, let us say at the kth degree, right, we applied the force at kth degree of freedom, and response is being measured at, let us say, jth degree of freedom, right. So, in that case this f of omega we can designate as f k omega, okay, that is the force at kth degree of freedom. Similarly, the excitation we have measured can be designated as a j omega. So, let us now obtain the frequency response function based on these measurements. So, since we have the excitation response, we will basically estimate the inertance. Inertance is based on the excitation response. So, inertance FRF it is given by A J K, that is the response, excitation response at the jth degree of freedom due to force at the kth degree of freedom omega. This will be now simply the ratio of A J omega and F K omega, right. So, this is basically the FRF for between the jth and kth degree of freedom. So, this is how the FRF between any two degrees of freedom can be obtained. Let us now look at what is impact hammer and what is basic construction. Okay. So, we are going to now look at impact hammer. So, this impact hammer is not a simple hammer, it is an instrumented hammer. Okay. It is an instrumented hammer, which means that it has been instrumented to measure the force that is being applied by the hammer. Let us try to sketch a diagram of the impact hammer. So, we have this here like this is the hammer head, right, and then in front of the hammer head we have a force transducer like this, okay, and then there is a provision to attach what is called as hammer tip here like this, okay, and then we have arrangement to hold the hammer like this. So, this is the handle, right, and then we have a output socket here, okay. So, therefore, let us do the nomenclature. This is hammer head, right, this is handle, this is output socket, this is force transducer, this is hammer tip, okay. And then there is also some designs have a provision of adding an extender mass here like this. So, one can add a mass here like this. So, this is extender mass. So, when the force is applied with the hammer, when the hammer is struck or hit against the structure, the force that is being applied is being sensed by the force transducer. Force transducer converts that to a proportionate charge signal, and if there is a built-in charge amplifier, that charge signal is converted to voltage signal, and that signal is then carried to the output socket through suitable cable. And then by connecting cable at the output socket, that force corresponding with that voltage signal can be measured. Now, the hammer tip is basically used in order to control or change the frequency of excitation that is basically excited by the impact, okay. And we will talk after this what is the role of hammer tip. Extender mass also can be basically added, right, to again reduce or change the frequency range of excitation. So, extender mass can be attached at the top or can be removed, and that basically helps to again little bit change the frequency range of excitation. So, these impact hammers are available in different sizes because different structures may require different amount of force for excitation. Small structures may require small amount of force. So, there are small hammers which probably can apply force maybe up to say 150 to 200 newtons, and then there are big size hammers which can be used for big structures like steel engine structures, requiring very large amount of force, like exceeding say 10 to 20 kilonewton, right. So, such hammers are also available. Let us now look at what is the role of hammer tip. So, typically manufacturers provide 3 or more tips, and they are typically we have a rubber tip, and plastic tip, and then we have say aluminum or metal tip. Okay. So, what is the role of this hammer tip, okay, in the excitation? To understand that, let us first of all look at the rubber tip and see that how what kind of impact it generates and what is the frequency domain, representation or frequency spectrum of the force that is being applied. So, let us look at rubber tip, right, and let us try to sketch a typical impact force that is being applied by this tip. So, this is force axis, that is force in newtons, right, and then so let us say this is up to say 400 newtons, right, and then we have let us say up to say 8 into 10 to the power minus 3 seconds, right, that is 8000 milliseconds. So, if with the rubber tip the force that may be applied may look something like this, right. This is the the force that is being applied, and so it is a very narrow pulse. So, we should note that it is spanning over say around 6000 milliseconds, right. So, it is a narrow pulse. Let us now try to see what is the frequency Fourier spectrum of this force signal. So, we take the Fourier transform and now we are going to plot the magnitude of the force in dB as a function of frequency. So, we are going to plot magnitude of force in dB, right, versus log omega, okay, that is on a logarithmic frequency axis, and the reference value used for finding the dB is the force amplitude at omega is equal to 0, right. So, at the 0 frequency, whatever is the force amplitude, that we use as the reference value to calculate the dB. So, let us try to sketch the spectrum that would result. So, this is nothing but the magnitude of f in dB, and then on this axis we have the frequency, right. So, this is say 10, then this is let us say 10 to the power 2, this is 10 to the power 3, this is 10 to the power 4, right. These are the decades of frequency ranges, and let us say this is 0 dB here, right. So, now if we plot, then this we see that the spectrum looks something like this. Something like this, right. So, what we observe? We observe that there is a main lobe here, this is the main lobe here, right, and then it is followed by side lobes. Okay, followed by side lobes. And we see that the main lobe has almost a constant magnitude, right, though it is not exactly constant because we are plotting on a dB scale. So, therefore, there is small change, but it looks almost constant, okay. And then as we go further, the side lobes appear, and the amplitude of the side lobes drastically reduces with frequency, okay. So, therefore, the excitation energy is mainly concentrated in the main lobe, and beyond the main lobe the concentration of the excitation energy is very insignificant, and because in that range the excitation energy is insignificant, the response in that frequency range is also very small, because of which the signal to noise ratio in that range is also small. Another thing we observe that between every two successive side lobes there is a frequency where the response is 0, right. The force may, because the force amplitude drops to 0 between every two at some frequency between every two successive side lobes. So, at those places in fact there is no response and only the noise in the signal would dominate. So, based on these observations we see that the effective frequency range which can be considered for FRF estimation is a range which covers the main lobe. Now, to decide the excitation frequency range we can use a thumb rule. So, the excitation frequency range is from 0 frequency, right, from 0 radian per second to the frequency where the force amplitude drops by 20 dB. Where the force amplitude drops by 20 dB. So, we can mark this somewhere here, let us say if this is minus 20, then if we extend this line, then now we can draw an ordinate here somewhere here. So, therefore, this we can consider as the useful frequency range over the structure can be assumed to be have been excited, right. This is the excitation frequency range. Okay. So, beyond this range, though there is some excitation, but that excitation is not adequate enough for making a reliable measurement. Okay, it is very small excitation is there. So, in this case we see that the range could be something like 200 or 250 hertz from this for this particular figure. So, rubber tip can be used typically to, depending upon the material of the tip, depending upon its dimension, the excitation range could be something like say 250 to 400 hertz or maybe in that range, right. Let us now see that how the nature of the tip affects the force profile and its spectrum. So, let us first of all draw the force profile here. So, here we have the force in Newton, we are plotting against the time, okay, and this is, let us say, the 8 into 10 raised to the power minus 3 seconds. And so, for the rubber tip already we had made the plot. So, this is around 400 Newton. So, this is for a typical medium size hammer. So, this is the rubber tip. If we use a plastic tip, we see that the length of the pulse becomes shorter and the amplitude of the pulse becomes larger. Okay. So, this is the force profile due to the plastic tip. Okay. So, this is due to plastic tip and this is due to rubber tip, and with a aluminum tip the force profile becomes even more narrower like this. Okay, this is aluminum tip. Okay. So, what is the observation? As the stiffness of the tip increases, right, because plastic tip has a higher stiffness as compared to rubber tip, and aluminum tip even has a more further higher than the plastic tip. So, as tip becomes stiffer, the force pulse becomes narrower. okay, and the peak force also becomes larger. Now, what is the effect of this on the frequency spectrum and the frequency range of excitation? So, therefore, we take the Fourier transform of all these three pulse signals, and let us now try to sketch an overlay of the Fourier spectrums, okay, of these three impact force profiles. So, here we are going to now show the magnitude of the force due to H in dB, right, and then we basically use the reference value for each of the spectrums based on the magnitude of the force at 0 frequency for the particular tip, right. So, reference values are different for each of the three profiles. So, therefore, finally, we have all the three curves starting from the 0 dB. So, this is in dB 0, and then let us say we have this is 10, this is 10 to the power 2, this is 10 to the power 3, and this is 10 to the power 4. This is in omega in radians per second. Okay, and now for the rubber tip already we had sketched this. Let us try to sketch that again. So, we have the spectrum like this. Like this. So, this is the spectrum due to the rubber tip. Now, let us try to sketch the spectrum due to plastic tip. So, this plastic tip spectrum will be, let us try to sketch a dotted line, use a dotted line to sketch this, and this is typically would be something like this. Something like this. Let us try to sketch it for the aluminum tip now, and this would be like this, right. So, this is for rubber tip, this is for plastic tip, and this is for aluminum tip. And let us now try to use our thumb rule to find what is the effective frequency range of excitation. So, we try to look at the cutoff frequency or the frequency where the magnitude of the force spectrum drops by 20 dB. So, if we sketch this line here like this, right, and then so what we see that this is the basically frequency range by of the rubber tip. So, we can call it this as omega rubber, and this is the frequency range of plastic tip, right, and this is the frequency range of aluminum tip. So, therefore, what we see is that as the pulse becomes narrower, the frequency range becomes larger. Okay. So, a stiffer tip will excite a higher frequency range. Okay. A stiffer tip will excite a higher frequency range, and therefore, the frequency range excited by the aluminum tip among the three tips is highest. Okay. So, we can say that as tip becomes stiffer, the frequency range of excitation becomes larger. So, if you let us look at these frequency ranges for a typical hammer commercially available, right, and which is used for excitation for medium or small size structures, then in hertz, if I quote these values, then for rubber tip this is around say 250 to 400 hertz, right, and for plastic tip this could be from maybe 2 to 2.5 kilohertz, okay, and for aluminum tip this could be like say 7 to 7.5 kilohertz. So, these are just approximate values basically indicating the order of magnitude of the frequency range of excitation, right, and the specific values they depend on the size of the tape, the material of the tape, right, even the stiffness of the structure on which it is hit, that will also affect the frequency range, okay. So, all these factors are going to affect the contact stiffness. So, effectively what is happening is the contact stiffness between the hammer and the structure, that basically alters the shape of the force that is being applied. Frequency range, they depend on, they vary from hammer to hammer and structure to structure. So, therefore, it is a good practice in model testing to first of all look at what is the effective frequency range one is able to obtain with a given hammer and a tip. So, one can perform a preliminary excitation and look at the force spectrum, and from that using for example this thumb rule, one can look at what is the frequency range that can be excited. So, now the question arises that should we use rubber tip at all, because aluminum tip has the highest frequency range of excitation. So, it will be able to cater to most of the situations. So, ideally we should use the hammer tip whose frequency range of excitation is just adequate to cater to the frequency range of analysis, right. Using a tip which has a much more higher frequency range of excitation will unnecessarily put a lot of excitation energy in the range which we are not interested to measure, okay, and therefore, the signal level in the useful frequency range or the desired frequency range will be reduced, and therefore, the signal to noise ratio will not be may not be adequate or enough, which will basically adversely affect the quality of our measurement. So, therefore, we should try to use that tip which just caters or is adequate to excite the frequency range which we want to measure. So, in this way today we looked at how excitation can be done using an impact hammer. We now stop here. Thank you.